All right, let's just jump right in. We're about to cackle one of the most bizarre, one of the most counterintuitive theorems in all of mathematics. Seriously, it's a result so strange that it feels like it breaks logic, common sense, and maybe even the universe itself.
You've probably seen a headline like this one floating around. And you know what? It pretty much nails the absolutely wild claim of the Banach-Tarski Paradox. The idea that you can take one solid ball, break it apart, and then put the pieces back together to get two identical copies of the original.
And that's the big question, right? Can a piece of pure math really let you create something out of nothing? Well, hang on, because we're about to unravel this mind-bending puzzle together. So, first things first, let's get crystal clear on what this theorem is actually claiming. And I really want to stress this. This isn't some wild guess or a hypothesis. It is a proven mathematical fact. The key here is that you're only allowed to do two things with the pieces: rotate them and move them. That's it. No stretching, no shrinking, no magical shenanigans. We're talking about rigid motions, the same stuff we do with physical objects every single day. But the result is anything but ordinary. And this isn't some fringe idea. It's a proven theorem inside the standard rulebook of math that basically everyone uses. And get this, we're not talking about some infinite, uncountable number of pieces. Nope. Back in 1947, a mathematician named R.M. Robinson figured out that the absolute minimum number of pieces you need to pull this off is just 5. That's it, 5 pieces. And this is where our brains start to short circuit. I mean, just moving an object around shouldn't change its volume, right? So if you take one sphere and rearrange its parts into two identical spheres, you've basically just proven that 1 equals 2, which, last I checked, is definitely not how math is supposed to work. So what on earth is going on? Well, like most things in life that sound way too good to be true, there is a catch. A huge catch. And the real secret to this whole paradox isn't in how you reassemble the pieces. It's all about the pieces themselves, which are, well, they're absolutely bizarre and physically impossible. So here's the crucial difference. The things we see every day, like a book or a coffee mug, they have a clear, defined volume. You can measure it. The pieces in this paradox, they're nothing like that. They are what mathematicians call non-measurable. You should think of them less like solid chunks of a sphere and more like an infinitely scattered, infinitely complex cloud of dust made of individual points. And this right here is the paradox's get-out-of-jail-free card. That whole contradiction about volume, it just vanishes if the pieces never had a well-defined volume to start with. You see, you can't violate the rule of conserving volume if the very idea of volume doesn't even apply to the things you're working with. Okay, so you might be wondering, how in the world do you even create these monstrous, non-measurable sets of points? Well, to do that, you need a very, very powerful and honestly a kind of controversial tool from the very foundations of mathematics. Say hello to the axiom of choice. It sounds pretty simple, right? If you've got a bunch of bags, you can just grab one thing out of each bag. Easy. But what if you have an infinite number of bags? This axiom lets you magically say, I can create a new set with one item from each of those infinite bags, but it gives you zero instructions for how you're actually supposed to make those choices. It just guarantees you can. It's this non-constructive power that makes the paradox possible. So how does this axiom of choice actually work its magic? Well, it's a process. First, you mathematically slice up all the points on the sphere into an infinite number of families. Then, the axiom of choice comes in like this magic key that lets you pick out exactly one representative point from every single one of those infinite families. That collection of points you just picked, that forms the weird, non-measurable blueprint for the final pieces. Without that initial act of choosing, the whole paradox just doesn't work. All right, now we're going to go one level deeper. Because it turns out, this paradox isn't really about spheres or geometry at all. No, at its very heart, it's about a strange, quirky property of the mathematics of three-dimensional space itself. So here's the real insight. This isn't about the shape of a sphere. It's about the math of 3D rotations. Think of the rules for how you can rotate things in 3D space as a kind of language. Well, it turns out that this language is so complex, so flexible, that it has a kind of loophole built into it. A paradoxical sentence structure, if you will. This loophole is what allows the duplication to happen on a purely algebraic level. The sphere is just the object we use to see this underlying mathematical glitch in action. And this is exactly why this whole thing is a 3D-specific problem. See, the group of rules for moving things around on a 1D line or a 2D plane is what's called amenable, which is just a fancy way of saying it's too simple, too well-behaved to allow for this kind of crazy paradoxical trick. But the group for 3D rotations, it's non-amenable. It has just enough weird complexity in it to contain that algebraic glitch we talked about, which is what allows the paradox to exist in the first place. Okay, so we have waded through some seriously deep mathematical water here. Let's pull ourselves back to shore and return to that original question. Can we actually use this to duplicate a pea or a sphere of gold and totally break physics? And the answer, of course, is a huge, resounding no, for a few really important reasons. First, real-world objects are made of atoms. You can't just keep dividing them forever to get to these infinite point sets. Second, physics has this very stubborn little rule called the conservation of mass. You can't just create matter out of thin air. These mathematical pieces, they're just abstract sets of points. They have no mass. And finally, the cuts themselves are infinitely complex. They're not something you could ever make with a physical knife. So, in the end, the Banach-Tarski paradox isn't a flaw in our math, and it definitely doesn't break physics. What it is a profound discovery. It's this incredible signpost that points to the strange, beautiful, and utterly counterintuitive things that can happen when you apply the logic of infinity to our ideas about space. It shows us just how far our physical intuition can take us and where it completely breaks down. But it does leave us with one last fascinating question to chew on. Is this whole paradox just a weird side effect of accepting the axiom of choice as a rule? Or, as some mathematicians have argued, could it be a hint that our most basic, point-based definition of what space even is might be missing something fundamental? It's a powerful reminder that even in a world as logical as math, the deepest truths are often the ones that feel the most paradoxical.